I'm going to leave as exercises a couple of things. The first one is this third example, which completes the proof for rotate. This is the case where we prove that whether you do the map before or after the reverse, you get the same result. And that follows a pattern very similar to the first two examples we've looked at. So I'll leave you to work through that for yourself. I'd also like to look at a more efficient definition of reverse, and this is defined using what's called a shunt function, and this is a tail recursive function. It shunts elements from the first list onto the second list and calls itself again. And what that does is if you put a list in the first argument, it terminates with the reverse list in the second argument and then returns that. And so what that does is gives us a more efficient, it's a linear rather than a quadratic list reverse function. Now we can prove a similar property here, but we have to think a little bit harder about how we define that. Because reverse is a particular case of shunt, the case where the second argument is empty, we might want to prove that an arbitrary shunt has the same, if you map a shunt of x's and y's, that's the same as shunting the map of x's and y's. So whether you map before or after the shunt, you get the same result. And we can prove that. It's slightly more complicated in that you have to prove at each stage, for each x, you have to prove the result holds for every possible value of y on the right hand side of shunt. And that's typical of the way that induction proofs work for tail recursive functions. So it's a bit more of a challenge, but I'll leave you to think about that too.